So we are going to see how the logical gates work in logically. First we'll see about AND gate. So we take two input, as AND gate has two input, and output we use the light bulb here, and we give the connections to AND gate and the output. This works in the combination of zeros and 1. If both the inputs are 0, there is no output. If one of the input is 1, there is no output. If both the inputs are 1, the light glows, so that means we get an output. Next, we have OR gate. Next, NOT gate. As NOT gate has only one input line, we took only one switch. In the case of NOT gate, if it is 0, we get an output, and if it is 1, we don't get an output. Next, XOR gate. Next, we have NAND gate. In NAND gate, there are two combinations, that is 2 input NAND gate and 3 input NAND gate. First 2 input NAND gate will have only 2 switches. In the case of 3 input NAND gate, we will use 3 switches. So to change the count, here there is a box called NAND gate properties, and input count you can change it to 3. So you'll get 3 input NAND gate, and you can get the connection using 3 switches. And last, NOR gate. In the case of any 2 inputs, we'll use only 2 power to 4 combinations, but in the case of 3 input, we'll use 2 power 3, that is 8 combination. Our next topic is adder and subtractor. In adder, we are going to see about half adder and full adder. In subtractor, we'll see half subtractor and full subtractor. In half adder, we will use 2 inputs, and we'll use a XOR gate and a AND gate. And we'll have 2 output. One output is sum and one output is carry. And we'll connect the A input to XOR and B input to XOR. Then another one to AND gate. An XOR gate is for the sum output, and AND gate is for the carry output. In the case of full adder, we will use 2 half adders, and we'll have 3 input, that is A, B and C. So we will use 2 XOR gate, 2 AND gate, and the OR gate. And same like half adder, we'll have 2 outputs, sum and carry. Next, half subtractor. We have two inputs and we will use OR gate, NOT gate and the AND gate. And same, we'll have two outputs, but one is difference and another one is borrow. And in the case of full subtractor, we'll use two half subtractor and we have three inputs A, B, C. Here we use two XOR gate, two NOT gate, two AND gate, and one OR gate. And we have two outputs, difference and borrow. And this is the logic diagram for half adder, full adder, half subtractor and full subtractor. The next topic is design and implementation of code converter 1. In that we are going to see how to convert binary to gray code and gray code to binary. The next topic is design and implementation of code converter 2. That is BCD to XS3 converter and XS3 to BCD converter. So we'll see the two topics together. So in code converter, so we're going to see two types of code converter. First thing is binary to gray code converter. Second is gray code to binary converter. Each will have 4 inputs and 4 outputs. Here we use 3 XOR gate, and also for gray code to binary we use 3 XOR gate. This is the logic diagram of converting XS3 to BCD and BCD to XS3. Our next topic is design and implementation of parity generator. For this we will need 3 input and 2 XOR gate and 1 NOT gate and 2 outputs. So we are going to connect the A input to one XOR and B input to the same XOR, and then we are going to connect that to another XOR and C input to that XOR, and one output is even and the other output is connected to NOT, and we get the other output as odd. So this is the logic diagram for design and implementation of parity generator. In multiplexer, demultiplexer, the first diagram is multiplexer and this diagram is demultiplexer. So in multiplexer we are giving 4 inputs and 2 serial inputs, which has S0 and it also has a NOT gate with it. So in the combinations will be 3, as we are using 3 input AND gate. So we'll give for example 1 0 0 and 1 0 1 combinations of 1s and 0, and then we'll add the 4 inputs and we get one output. From 2n input lines we are getting one output line. In the case of demultiplexer we are giving one input line and then 2 serial inputs, then we are getting 2n output lines. So for SR flip-flop, we take a SR flip-flop and then we have 2 inputs S and R and a clock signals which keeps on changing, and then we have 2 outputs Q and Q dash. Q is the present state and Q dash is the next state. Same as for JK flip-flop, here we have 4 conditions, that is J, K and precondition and then clear. So Q is the present state and Q dash is the next state, and here also we use the clock signals, and same for the D flip-flop. But for SR flip-flop and JK flip-flop we use 2 inputs, whereas here in D flip-flop we use only 1 input and precondition and clear, and we have QQ dash as output. Thank you.